Welcome to Module 7, which is all about thermodynamics and state functions. Okay, so this is kind of a long section, but bear with me. It's going to be a lot of information, but hopefully you'll be able to have a much better understanding of all the different types of thermodynamic relationships that you'll see in chemistry. So there are different ways to represent energies in a system, and chemists kind of view the universe in a pretty simple way. Okay, and so the first thing that we care about is the system. So the system is maybe a chemical reaction or a container, right? A very specific thing. Okay, everything else that is surrounding the system is called the surroundings. And then the boundary is what separates the system from the surroundings. Okay, and so there are three things that we sort of have to worry about: the system, the surroundings, and the boundary. The default, unless you hear anything, is that we care about the system. Okay, so the implication is that the thing we're looking at first is the system. Okay, what's happening to the reaction or to the reaction vessel, right? Whatever the reaction is taking place in. So let me give you some basic definitions. Okay, work is any kind of motion that goes against some kind of force. Okay, and so you can think of work as some kind of force being done in a certain direction. Okay, heat is more along the lines of temperatures, right? Energy changes associated with changes in temperature. So there are certain words that are associated with changes in heat that you may have heard already: exothermic and endothermic. Okay, exothermic reactions release heat, right? Give them off to the surroundings. Endothermic reactions absorb this heat from the surroundings. So there are different kinds of energies that we care about. The first one is called internal energy. Now, depending on the book that you're using, you might say the letter U or the letter E. E is more commonly used. Okay? Internal energy represents the total energy of the system, which is really the sum of the kinetic energy and the potential energy. Okay? The good news about energies is that they're all state functions. So what exactly is a state function? State function is something where the path that I take to go from one part to another part doesn't matter. Okay? Unlike kinetics, which was module 6, where the way that I go from A to B matters, okay, none of these things have that problem. Okay? For any kind of thermodynamic variable, however I go from A to B is irrelevant. Okay? So let me draw you a little picture. Okay? Let's pretend that I am here and I want to get here, right? This is my house. So one thing that I can do is go straight this way. That might be the fastest way. But maybe I have roads and streets and things and I have to go this way. Or maybe I have to go this way. Or maybe I had a little bit too much to drink and I sort of have to go this way. Okay? If all I really care about is getting home, the path that I take doesn't matter. All of these are the same. These are state functions. Okay? But clearly, it's a lot more work for me to stumble around and take this very circuitous path than to do the very direct path. Okay? So it turns out things like heat and work are not state functions, but internal energy is a state function. Because it's a state function, there's a very useful property that I can use, which is that the change in internal energy, okay, is equal to the final internal energy minus the initial internal energy. I only have to worry about 2 points, the final and the initial. I don't have to worry about all of the other points in the middle. Whereas for things that are not state functions like heat or work, not only do I have to know where I start and where I end, but I also have to worry about all of the intermediate points as well. Okay, and so we're going to deal with state functions because they're much easier. I only need to know 2 things: where I'm starting and where I'm ending. Another type of energy is something called enthalpy. Enthalpy is given the letter H, and enthalpy is used to represent just the potential energy of the system. Okay? So we're not looking at kinetic energy, but just potential energy. Enthalpy, like internal energy, is also a state function, which means that the change in enthalpy is going to be just the final minus the initial, okay, delta H. So as you saw earlier, if something is exothermic, delta H is negative, less than 0. And if something is endothermic, delta H is positive, greater than 0. All right, this brings us to something called the first law of thermodynamics. There are different ways to state the first law of thermodynamics. Okay, one way is that the total energy of an isolated system is constant, which means that there's a conservation of energy, right? The total energy is not changing. Even though that's true, that doesn't mean that the kind of contributions to that energy are always the same. Okay, and so we're going to assume that the internal energy of the system can change due to some kind of change in heat and or some kind of work that's being done. Okay, heat transfer and work that's being done. Those are the two things that we worry about, heat and work. And so we can say that the total change in the internal energy is just the sum of the heat and the work. Okay, change in internal energy, delta U or delta E, is equal to Q, the heat, plus the W, work. Okay, so heat plus work. Those are the only ways that I can change the internal energy of a system. First law of thermodynamics could also be interpreted as any changes happen to the system, there has to be an equal and opposite change to the surroundings, right? So if the system gains energy, that energy had to come from somewhere, and the somewhere is the surroundings. Okay, and so if the surroundings lose energy, the system gains energy. But the total energy of everything combined, system plus surroundings, sometimes called the universe, or the total change in internal energy, has to be exactly 0. Okay, and so delta U of the system plus delta U of the surroundings has to equal 0. Just in case you might see a different convention in textbooks or other sources, sometimes you'll see the first law of thermodynamics written as delta E equals Q minus W rather than Q plus W. So what's the deal? Well, it has to do with the convention for how work is defined and how heat is defined. So heat is assumed to be positive, right, greater than 0, if it's being absorbed by the system. And heat is negative, less than 0, if it's being released by the system. That nobody really has any problem with. Everybody defines heat the exact same way. The problem is work. Okay, and so chemists and chemical engineers and other like-minded folk have what I call the greedy convention, meaning it's all about the system, right? You have to think about it from the system's point of view, okay? And so if the system is doing work, that's bad, right? Who the heck wants to work? So in that case, work is negative. But if work is being done to the system, that's very nice, right? It's nice when people do work for you. So there, work is positive, okay? In other subjects, like maybe physics, they have a bit more of an altruistic interpretation, okay? And so for them, the signs are flipped. Work done by the system is positive, and work done to the system is negative. That's why sometimes you'll see it as Q minus W instead of Q plus W. But it's really the same idea. So now let me show you something called Hess's law. Hess's law is a direct consequence of the fact that these variables are state functions, okay? Because it's a state function, it doesn't really matter how I go from A to B. All that matters is where A is and where B is, okay? And so if I want to find the total change in enthalpy for a reaction, okay, I can do that by taking any path that I want, including just looking at sort of individual heats of formations for separate compounds or substances. Okay, and so I can take enthalpies for individual reactions, even if they're not actually taking part in the process, right? I can pretend that these things are happening. As long as I start and end at the same spot, delta H will be exactly the same, okay? The other nice thing about Hess's law is it's not restricted to just enthalpy. Any state function will obey Hess's law. So I can do this for internal energy, I can do it for enthalpy, and you'll see later, I can also do this for things called entropy and Gibbs free energy. All of these things work exactly the same way. So now let's talk about phase changes or transitions, okay? What is happening during a phase change or a transition, okay? This is when, for example, you go from like solid to liquid or liquid to gas, right? We talked about phase changes earlier. all of these changes in phase are also going to have a change in enthalpy because the potential energy is changing, right? Solids and liquids and gases and all these different phases have different levels of potential energy associated with them, okay? Typically, solids tend to have sort of less, and gases tend to have the most energy associated with them. So let's pretend that if I'm going from A to B, there's a certain change in enthalpy delta H. If I go in the opposite direction, right, from B back to A, the change in enthalpy is just going to be minus delta H. Same magnitude, opposite direction. Again, this is a consequence of it being a state function. Now let's say that I did something from A to C, okay? Even if I only went from A to C in one step, I could pretend that I went from A to B and from B to C and add them up, okay? And so delta H going from A to C has to be exactly the same as delta H going from A to B and delta H going from B to C, because, again, Hess's law. So if I have an actual chemical reaction, I could think of the change in enthalpy for this reaction, or standard reaction enthalpy, as the changes in enthalpies between the products and the reactants when they're in their standard states. Okay, and so I can write this as a pretty nasty looking equation, but I think you'll see that it's actually not that bad to use. I just have to consider what the enthalpies are of the products and the reactants and whatever the balanced coefficients are in the chemical reaction. Okay, and so what I can say is that delta H for the reaction is equal to the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. And the little n's here represent the coefficients when I balance the chemical reactions. The little circles on top here indicate standard state. Okay, so standard state means that I have a temperature of 25 degrees Celsius and a pressure of 1 atmosphere, or more precisely, 1 bar. So now let's talk about the second law of thermodynamics, right? First law talks about conservation and changes in internal energy due to just heat and work. Second law is a little bit different, okay? It doesn't really have to do with conservation of energy, but more about like the direction or the flow of energy, okay? We use it to predict what's called spontaneity, or a tendency for a process to happen naturally, okay? So here are some examples of things that you've probably come across in your daily lives that you may not have thought of in terms of thermodynamics, okay? If the only thing we had going for us was the first law, everything would be reversible, right? You can go backwards just as easily as you can go forwards. But you may have noticed that there are certain things in life that only seem to go in one direction, okay? So for example, if you take a ball and you drop it, okay, it'll bounce. But you never see a ball that's on the ground just like spontaneously go up and hit you in the face, okay? Or if you have kind of a very expensive vase or glass and you shatter it by accident, and it breaks into a million pieces. That happens pretty commonly, but it's impossible for all of these little pieces of glass to sort of spontaneously reform into the original vessel or the original glass, okay? Or if you take maybe yellow paint and blue paint, you can combine them to make green paint, but you almost never see sort of green paint being spontaneously separated into those two colors, okay? There's like a certain direction for these things to happen. So all of these things are examples of directionality or spontaneity. And so these are associated with the second law of thermo, which really has to do with changes in entropy. So the second law talks about what's called the distribution of energy, not the total energy. And the second law of thermodynamics basically says that energy tends to go in a direction where things are going to be more spread out or dispersed or diffuse. So here's another way to think about the second law of thermodynamics. The entropy of an isolated system, meaning something that's by itself, only has to go up in the course of a spontaneous change. Okay, so we're going to use the letter S for entropy. Total change in entropy of the universe has to be greater than 0, positive. Okay, and so we're going to think about entropy as things like chaos and randomness and disorder. Okay, you can calculate entropy by looking at things like heat. Okay, so even though heat itself is not a state function, entropy is. Okay, and so I can still convert something that is not a state function to something that is a state function. Okay, so it's going to turn out to be the case that if I take the Q, the heat, and divide it by the temperature, I can get an entropy change. Okay, and so delta S is equal to Q over T, assuming that things are done at constant temperature. So let me show you how this works. Okay, in the specific case of a phase transition where things are happening at a constant temperature or at a constant pressure. Okay, if the phase is changing, but everything else is constant, okay, the change in heat or the heat transfer is equal to the delta H, the change in enthalpy for this transition. And since delta S was equal to Q over T, that also means that delta S is just delta H over T. And that's what I've got here. So delta S for the transition is going to be delta H for the transition divided by the temperature of the transition. Okay, and so if I know what temperature this is taking place at, I can also figure out the change in entropy for the process. Okay, so just as an example, let's say you were going from solid to liquid, right? Also known as melting or fusion. So I'm going from solid to liquid. That's an endothermic process, right? I have to add energy to melt something, to go from solid to liquid. So because my delta H is positive and my temperature is positive, when I divide those, I have to have a positive value for S, right? So my entropy is increasing. This is why people say that liquids have a greater entropy than solids, right? They're more random, more chaotic. Similarly for gases, right? Gases have a greater entropy than liquids do, okay? But if we're going the opposite direction, maybe I was freezing something and going from liquid to solid, in that case, my delta H is negative, and then my delta S is also going to be negative. That has a lower entropy. So how do I calculate or measure entropy? Well, pretty much the same way that I do it for enthalpy. I can define delta S for the reaction, change in entropy for the reaction, as being equal to the sum of all of the entropies of the products minus the sums of all the entropies for the reactants. Okay. Once again, the little circles mean standard state. The big difference here is I'm using S and not delta S, whereas for enthalpy, I use delta H. Okay, this is because we can't really assume that entropies are ever zero unless temperature is absolute zero. Okay, I can define an enthalpy of a reaction as being equal to zero. Okay, that's pretty common, right? All of the heats of formations for all of the elements in the periodic table are exactly zero, or for naturally occurring diatomic molecules, they're equal to zero. But entropies are not zero unless I'm at 0K, absolute zero. Okay, and so that's kind of the big difference between this one and the one for delta H. So now let's talk about the last thermodynamic variable here, Gibbs free energy. Okay, this is probably the most famous thermodynamic expression or relationship. Okay, and so Gibbs looked at changes in enthalpy and changes in entropy and put it all together. Okay, and so here's the idea. Enthalpy represents the potential energy of the system, all of the energy that's stored inside all of these bonds. Okay, but just because I have all of this energy being stored potentially doesn't mean that I can use 100% of it. I have to reserve some of it to fight entropy, right? Think of entropy as my enemy. Okay, I have all this energy with me, but I need some of it to defeat entropy. The amount of energy that I have left over or free after I've conquered entropy is this Gibbs free energy. Okay, and so it's the total potential energy H minus T times S, right? The temperature times the entropy. Or if I'm dealing with changes, okay, delta G is equal to delta H minus T delta S. Okay, this leads to the familiar conclusion that if I have a spontaneous process, delta G is going to be negative, right? Less than zero. So if delta G is less than zero, this is spontaneous. Delta G is greater than zero, this is non-spontaneous. And if delta G is equal to 0, guess what? I'm at equilibrium. Okay. You could think of delta G as representing the maximum work that can be done by a system that isn't considered PV work. PV work is simply expansion of a gas in some kind of piston where the pressure and the volume might be changing. Okay, and so if I disregard PV type work, everything left over after that is delta G. Okay. How do I measure delta G? Well, pretty much the same way I've measured delta H and delta S. I can report delta G for a reaction as being equal to the sum of the Gibbs energies of formations for all the products minus the Gibbs energies of formations for all the reactants. Okay, once again, everything has to be in the same state, standard state, and just like enthalpy, all of the Gibbs energies of formations for all of the elements are going to be 0 at standard state. Okay, so that makes life a little bit easier as far as calculations go. Experimentally, sometimes I get delta G by examining or determining delta H and delta S separately. Okay, because I can also say that delta G is equal to delta H minus T delta S. So if I don't know the Gibbs energies of formations, but I know the changes in enthalpy and the changes in entropy, I can still figure out delta G. Okay. So what does delta G represent? You can think of it as being the difference in the Gibbs energies of the reactants and the products in their standard states. And when you talk about differences in energy, that kind of also brings into mind things like equilibrium, okay, and equilibrium constants. Remember, those were related to the concentrations of the products and the reactants in their standard states. So you might say to yourself, I wonder if there's some kind of relationship between delta G and this equilibrium constant. And the answer is yes, there is. Okay, there's a very useful equation that relates the changes in the Gibbs energy to the changes, or excuse me, to the equilibrium constant. And so that equation is shown here. Delta G for the reaction, or delta G0 for the reaction, is minus RT times the natural log of K. This is the crucial link between thermodynamics, or energies, and equilibrium. Okay, notice something interesting that happens. Okay, if my equilibrium constant is greater than 1, which means that the products are favored compared to the reactants at equilibrium, then I have a negative value for delta G, 0 for the reaction. And if K is less than 1, then the natural log is going to be negative. When I multiply the negative of the natural log by the negative in the minus RT term, that's going to give me a positive value overall. So that's going to give me a delta G0 greater than 0. Okay, and so I can figure out what I'm predicting for delta G based on K, right? If K is greater than 1, delta G0 should be less than 0. And if K is less than 1, delta G0 should be greater than 0. If I do things under non-standard conditions, right? Maybe the temperature is different or the concentrations are different. The good news is that I can kind of convert or compare the delta G for the reaction to the delta G standard. And I can do that by using this equation down here. Delta G for the reaction under any circumstances is equal to delta G0 for the reaction, right? This is standard state, plus RT times the natural log of Q, where Q is something called the reaction quotient. So let me show you something interesting. Okay, if I'm at equilibrium, then Q, the reaction quotient, really becomes K, the equilibrium constant, and as we talked about earlier, delta G for the reaction is equal to 0. So if I take those results and plug them into this expression, I get 0 equals delta G0 for the reaction plus RT ln K, and then all I have to do is rearrange this a little bit. Delta G0 equals minus RT times natural log of K. Okay, and so this is exactly what I showed you over there. Okay, and so that's where it comes from. This is what allows me to relate equilibrium constants to changes in the Gibbs energy.